Okay, good morning to everyone. Good afternoon. This time is 13 hours here in Argentina. My name is Luis Avilés, and we are in the third session of our seminar series of the Magnetic Resonance Laboratory. In this time, we have an invited talk from UCSD, University of California, San Diego, and is Chunhui Du, who is giving you our talk, the talk entitled Quantum Sensing of Quantum Materials. Okay. A bit of the background of Chunhui. She's an assistant professor at the UCSD in California. She received her bachelor degrees in physics from East China Normal University in 2010, and her PhD in physics from the Ohio State University in 2015. After that, he did a postdoc. He was a postdoctoral fellow at Harvard University before joining UCSD in March 2019. Actually, or her current research line focus on the development of color center-based quantum sensing technologies for studying emergent condensed matter system. She has received numerous prizes, including the National Science Foundation Career Award in 2021, the Air Force Office of Scientific Research Young Investigator Award in 2021, also the Department of Energy Early Career Award 2022, the Office of Naval Research Young Investigation Award this year, and the International Union of Pure and Applied Physics Early Career Scientific Prize in 2022. So, Chunhui, the audience is yours. I will stop sharing my screen now, and you can share yours and start whenever you want.
All right. Yes, thanks very much for the nice introduction and the invitation from Luis that gave me such a great opportunity to talk about the research efforts in my group. So I'm Chunhui Du. You can also call me Rita. I joined U San Diego Physics Department as assistant professor in 2019, and currently in transition to Georgia Tech. I would like to talk about the research efforts in my group to develop quantum sensing and imaging techniques to study quantum materials. As you can see on the slides, we are working on diamond. That's our research tool, and you may feel surprising because we typically see diamond on very expensive engagement ring. However, we find that's the best friends for our research. So first, let me talk about and introduce the research tool in my group. We work on diamond, and we know that diamond can contain a variety of colors. For instance, red, yellow, and blue. The color results from the defects in the diamond. For instance, these tables summarize a variety of color centers in diamond that generate light in different wavelengths. And the color center I will talk about today will be make diamond pink in color. That's called Nitrogen-vacancy center, NV. And NV center is formed by replacing carbon ion in diamond by nitrogen and removing a nearby carbon ion, so it creates a vacancy. So this forms a spin-one entity, and we can use this to serve as a quantum memory for quantum computation and information application. Also, you can think of this as an atomic scale sensor in diamond that allows nanoscale quantum sensing applications. So quantum information and quantum sensing are two main applications of color centers in diamond. And basically, over the past decades, there is ongoing research to investigate other color centers with accessible spin that shares very similar properties as NV center, and some has even better property than NV center as some conditions. For instance, silicon vacancy center in silicon carbide or diamond, as well as color centers in two-dimensional materials such as boron vacancy center in hexagon boron nitride. So those color centers has similar properties as NV center. So in my talk, I will start from NV center to talk about the application of it in the area of quantum information science. Then later in my talk, I will also discuss our effort to develop color centers beyond NVs. First, let me introduce the field of quantum information science, and it is an emergent field that can bring revolutionary changes to sensing, computation, and computing. So unlike conventionally computer that stores information in binary bits like 0 and 1, quantum computer stores information in the quantum superposition state. So the quantum state can be represented using the block sphere showing here. So 0 and 1 state represent the north and south pole, and a quantum state can be represented by any location on the surface of the block sphere. So this significantly improve the storage capacity and a quantum memory, like a two-level system that can serve as a quantum memory, is also called quantum bit or qubit. So for quantum information science, one of the most important research direction is to develop and understand quantum system that can serve as a qubit. So here I list several quantum systems that can potentially serve as a qubit, including one of the mostly widely studied systems, superconducting qubits, and also trapped ion system that is the research focus of the MO, and also silicon quantum qubits, semiconductor-based quantum qubits, as well as topological qubits, and the color centers in diamond, including NV centers in diamond, as well as optical photons. So each qubit system has its own advantages and disadvantages. So in my talk, I will first discuss some of the advantages of NV center as a qubit. And then also I will discuss some challenges in this field later in my talk. So most qubit system requires working at very low temperature, like millikelvin or even nanokelvin temperature. So qubit as NV center in diamond can work at relatively high temperature, including room temperature. And also, qubit system is typically very sensitive to the external environment, so it's sensitive to the noise. Like for instance, superconducting qubits, the lifetime of the qubit is on the range of microseconds. It's really short. Trapped ion system has one of the longest qubit coherence time, and NV center also has reasonably long coherence time for quantum operation. And also because it's a color center, so it can couple with optical photon to form quantum network for quantum communication application to transfer information between two distant quantum operators. And also because NV center is a atomic size qubit, so it's enable high qubit density, like nanoscale qubit density, and also enable nanoscale quantum sensing. Other qubit system, the size may be larger. For instance, superconductor qubits, the size is typically on the range of a few hundred micron to millimeters. So high qubit density is also another advantage of NV center-based qubit system. Right, so in my talk, I will first discuss about the research activities in my group. So based on the advantage of the NV center-based qubit and the qubit based on color centers with spins, my research combines basically the two applications of the color centers. First, we use it to develop the state-of-art quantum sensing and imaging techniques to study a broad range of quantum material, including topological material, superconductor, and the two-dimensional materials. And another application of qubit is that we can combine the qubit system with spintronic devices that's engineering hybrid quantum system for quantum information application that allow efficient control of the qubits. In my talk specifically, I will use 4 research projects in my group to discuss the applications of color centers in the area of quantum information science. First, I will talk about quantum sensing application, and then I will show you that NV center can be used as a nanoscale quantum sensing and imaging platform to study various antiferromagnetic material, including the antiferromagnetic insulator, as well as non-collinear antiferromagnetic wires and metals. And also, I will talk about our efforts to develop quantum sensors in 2-dimensional material that has the potential to achieve atomic scale detection sensitivity and image resolution. And finally, I will show you our efforts to develop hybrid quantum devices combining the color center spin qubits with spintronic system that can allow voltage control of the spin qubit for quantum information application. All right. First, let's look at the quantum sensing application. That's one of the most important application of NV center. And as we know, NV center is a single electron, basically like a spin-1 entity. And then as a spin-1 entity is sensitive to various physical properties, for instance, magnetic field, temperature, pressure, and electric field. So it's actually a multimodal quantum sensing platform that we can use to study quantum material. And especially our quantum sensing of quantum material benefit greatly from the magnetic field sensitivity. And now I will explain the mechanism. So NV center has 3 energy levels depending on the spin orientation along the quantization axis, which is ms0, ms-1, and a +1 state. And the unique thing about NV center is we can initialize and read out a spin state optically. So by shining a green laser, NV center will generate red photoluminescence, and it will be spin dependent. So when it's at 0 state, it's bright. If it's at plus and the -1 state, it's darker. And the zero field splitting frequency is about 2.87 gigahertz, and it can be goes through the Zeeman splitting if we apply external magnetic field. So during our experiment, we can monitor the photoluminescence generated from the NV center as a function of microwave frequencies. So when the frequencies matches the NV electron spin resonance frequency, NV spin will flip from 0 to one of the other spin state, and this leads to a decrease of the photoluminescence. And from the separation of the -1 and the +1 state, we can read out the static field at the NV location. So we can use this method to image the stray field generated from the spin texture of the quantum material, or the Earth field generated from the current in the material. If we measure the zero field splitting frequency, it couples with the lattice constant of the diamond lattice. So this enables sensing of the temperature using NV center. So the zero field splitting frequency of NV center will change with the external temperature in a well-known fashion. So this allows us to also study thermally driven phenomena, for instance, study like spin charotronics based or other thermally driven phenomena based on NV center. And in addition to static field and temperature, NV center is also sensitive to microwave field. For instance, it's sensitive to coherent microwave field. And when a coherent microwave field is applied at the NV electron spin resonance frequency, for instance, at the frequency of the 0 to -1 spin transition, if we vary the duration of the microwave field, the NV spin will in the rotating frame, the NV spin will rotate about this external applied microwave field periodically, so it will rotate between 0 and -1 state. So if in this case, if we monitor the photoluminescence as a function of the duration of the microwave field, we can see that it will follow the Rabi oscillation, which is because MV spin is rotate between 0 and -1 state periodically. And from the frequency of the Rabi oscillation, we can measure the local microwave field at the NME location. So this allows us to measure the amplitude and phase of microwave fields, and also study the magnetic resonance or ferromagnetic resonance of the quantum material. In addition to coherent microwave field, we can also use the NV center to measure non-coherent microwave field, for instance, magnetic fluctuation, like magnetic noise. And this take advantage of the NV relaxation rate experiment. So in this case, we can initialize the NV center at the 0 state, and then we can monitor how long it takes for the NV center to relax to the mixed state in a noise environment. So we will see that photoluminescence will follow the exponential decay as a function of the delay time, and the relaxation rate will be proportional to the noise at the NV location. So this allows us to measure the spin excitation, like spin dynamics, as well as the charge excitation, for instance, Johnson noise, to study the electrical conductivity of quantum material. So then I will talk about how we can use those multimodal quantum sensing and imaging platform to study quantum material. And as we study the quantum material, our spatial resolution and the image sensitivity is determined by the distance between the NV center to the material. So it's critical to ensure nanometer scale NV center to material distance. So we realize that our group developed several state-of-art quantum sensing and imaging platform to achieve nanoscale sensor to sample distance. And wide field imaging is one of the most convenient way for quantum sensing and imaging application. So in this case, we can implant the NV center few nanometer below the diamond surface. And then we can transfer the material, for instance, nanoflake, or grow the material directly on diamond, and then using ensembles of NV center to achieve a wide field, so we can detect the photoluminescence using a camera, and so we can get a wide field imaging of NV center ensembles and use that to study the local properties of the material. So sometimes the material cannot be directly grown on diamond. For instance, complex oxide material may require a lattice match substrate for the epitaxial growth. So in this case, we can pattern diamond nanostructure containing NV center and transfer it on the material surface. So this includes patterning the diamond into diamond nanobeam with the width around micron size, or pattern the diamond into microstrips and transfer it on the material surface. So we can also use a fabricated diamond cantilever containing a single NV center at the end. Then we can attach this diamond cantilever to atomic force microscope, so we can scan the tip on the material surface to achieve a magnetic imaging. So for wide field imaging, the spatial resolution is about 500 nanometer, limited by the optical diffraction. And for scanning probe-based NV imaging, the spatial resolution is around tens of nanometer. So that's the best among other quantum sensing platforms. So in my talk, I will discuss the application of NV center using various different kinds of quantum sensing platforms. So first, I will talk about our efforts to use MV Center to study antiferromagnetic material. And I will show you two examples. So for first example, we use MV Center to detect spin fluctuations and to study the transport properties of the antiferromagnet non-invasively. And in the second example, I will talk about the scanning probe-based MV imaging to study the non-collinear antiferromagnetic domains of white side metal -13 with tens of nanometers spatial resolution. So antiferromagnet is a very important material system for next generation spintronics application because it's very robust against magnetic field and the external perturbation, and also because the magnon energy of antiferromagnet is typically very high due to large anisotropy and exchange field. So this leads to ultra-fast data for processing based on antiferromagnet. And also recently, pioneer work shows that the spins in antiferromagnet can transport over a long distance as long as 10 micron, so which is promising for long distance dissipation, low dissipation information transfer. So for the state-of-art measurement of the spin transport properties, typically it takes advantage of this non-local measurement geometry. So we have a material and we pattern two metallic strips on top of the material. So we use one strip to inject the spin using the spin Hall effect or the thermal gradient. Then the spin will diffuse inside of the material, and we can detect the spin accumulation using the inverse process of the injection, using inverse spin Hall method, for instance. So this has been applied to a broad range of material systems, for instance, alpha iron oxide, as well as like two-dimensional material system that can potentially host spin superfluidity. However, this device is really sensitive to the interface quality between the metallic system and the material. So it's hard to control in miniaturized devices. So we want to see that whether MV Center as a local probe can be used to measure the spin transport properties in antiferromagnetic material locally and non-invasively. So typically it's very hard to study antiferromagnetic material system because if you have a compensated antiferromagnet due to the antiparallel spin configuration, it generates a zero stray field. So we cannot use magnetometry to measure the antiferromagnetic easily. To imaging it, it will require some uncompensated surface spins, which is typically also very small, or it requires that the material hosts non-collinear antiferromagnetic detector like at the domain wall, or it hosts non-collinear antiferromagnetic domains. So I will talk about the imaging of this type of antiferromagnetic material later in my talk. So for fully compensated antiferromagnet, it has zero static stray field. However, it still allows development of finite spin fluctuations. So we can use MV Center to measure the spin fluctuation and to study the antiferromagnet. So if we look at the spin diffusion equation, the spin current is determined by the spin diffusion constant and the gradient of spin density. So spin diffusion constant is one of the very intrinsic spin transport properties, which is essential for us to understand how the capability of the material to transport the spin current. And also, if we look at the time-dependent spin density, we can see that the time-dependent spin density is also correlated with the spin diffusion constant. So if we use MV center to measure the time-dependent spin fluctuation of the spin density, we can directly review the spin diffusion constant by solving the spin diffusion equation. So this is our mechanism. So next I will show you that indeed we can use MV center to measure the spin diffusion constant, and because we measure the fluctuation of the spin density in thermal equilibrium condition, so this means that we can measure the spin transport properties non-invasively without making electrical contact to the material. So this is our measurement platform. So the material is called alpha iron oxide. Is the material system that has been discovered using the spin transport measurement that it has long spin decay length. And at low temperature, this material is uniaxial antiferromagnet. So there is no net moment, and the two spin silver lattices are antiparallel to each other. So measure the spin. In order to measure the spin fluctuation, we transfer the diamond nanobeam containing MV center, containing a single MV center, on top of the material surface. And in order to understand the spin fluctuation, we can use this schematic. So we can separate the spin fluctuation into two main categories. The z-axis here is the near order. So we can separate the spin fluctuation into the transverse spin fluctuation that are happening perpendicular to the near order, as well as the longitudinal spin fluctuation that's parallel to the near order. So you can see that the transverse spin fluctuation has the same frequency as the antiferromagnetic magnon. So in the alpha iron oxide, the band gap of the magnon is about 160 gigahertz. So this frequency is much larger than the few gigahertz NV electron spin resonance frequency. So we basically cannot probe the transverse spin excitation using MV center. However, the longitudinal spin fluctuation is actually gapless. So those low frequency excitation can actually match the MV electron spin resonance frequency and increase the MV spin relaxation rate. So if we measure the MV spin relaxation rate induced by this longitudinal spin fluctuation, we can probe the spin diffusion constant. So according to the theoretical model that's based on our collaborator, Yaroslav Chefanek and Benedetta Flappus, we can see that the longitudinal spin noise shows very strong frequency dependence. So it's strong at low frequency, then decreased with increasing frequency. And in our measurement, we can vary the external magnetic field. So this allows us to change the NV electron spin resonance frequency. So we can use that to probe the frequency dependence longitudinal spin noise. So here we can see our measurement result shows that the NV relaxation rate indeed change with the NV electron spin resonance frequency in expected way. So it's decrease with increasing frequency. So by fitting this frequency-dependent relaxation rate, we can extract the spin diffusion constant that's about 9 × 10⁻⁴ meters squared per second at 200 Kelvin for the alpha iron oxide. So to further understand what does this spin diffusion constant mean, so we can, using that, we can estimate the spin decay length, which is the square root spin diffusion constant times the spin relaxation time. So if we estimate the spin relaxation times, it's around 10 × 10 nanoseconds. That's typically for magnetic material. So we can see that the spin decay length is about 3 micrometer, and this length scale is also kind of in agreement with the transport measurement result using the non-local measurement geometry based on alpha iron oxide. So this confirms the validity of our method. And we also want to highlight that because in this case, we measure the spin relaxation rate of the NV center in thermal equilibrium conditions. So it's a non-invasive measurement to study the spin transfer properties. And also, because our measurement is very general, we don't need to pattern the electrode using the nanofabrication technique. So this allows us to study material system with short spin decay lengths relatively, and with large energy gap. For instance, two-dimensional ferromagnetic and antiferromagnetic material, as well as spin liquids. All right. So next, I will show you our measurement of the antiferromagnetic wires on metal, manganese-13. So manganese-13 hosts non-collinear antiferromagnetic moment in the Kalman lattice. And it has a very weak moment compared with the ferromagnetic counterpart. However, people find that although the moment is very weak, it still gives sizable anomalous Hall effect, and this is attributed to the Y node at the Fermi surface. And also, in addition, another exciting research direction is that people find that we can electrically control and read out the spin state of the manganese-13 by sending an electrical current to the heavy metal ground on top of it. So we can read out the switching of the magnetization from variation of the anomalous Hall effect. So there is ongoing research to understand the mechanism of this current-driven spin dynamics of the manganese-13. So many mechanisms has been proposed, for instance, like spin orbit torque or Joule heating, as well as the intergram spin transfer torque. So in our study, we will use NV center as a local probe to understand the mechanism. So this is our measurement platform. The film is 50 nanometer, like a manganese thin film, and it's a polycrystal. So it contains various non-collinear antiferromagnetic domains. And this domain give rise to variation of the stray field that can be imaged using a single NV sensor contained in the diamond cantilever. So this is our stray field imaging. We can see that manganese-13 gives rise to nanoscale magnetic domain with the dimension about 100 to 200 nanometer. And here the spatial resolution is about 50 nanometer, determined by the NV to sample distance. So then we will monitor the electrical controllable spin configuration of the manganese-13. So we pattern the device into a whole bar structure, and then we send the current into the heavy metal ground on top of the manganese-13. And this will lead to switching of the magnetization of manganese-13 that can be read out from the variation of the anomalous Hall effect. So from the anomalous Hall effect, we can see that indeed the spin speed of the manganese-13 are switched between two states. Then we will study the current dependence of the NV imaging. So we focus on the cross area of the domain, cross area of the whole bar devices. So at zero current, we get magnetic imaging, so which is like this. Then we will monitor the current dependence of the magnetic state. So here, the zero current imaging was subtracted from the 4 imagings here to highlight the changes of the magnetic state. So we can see that at point B, below the critical current, nothing changes. Then as we increase the current, the magnetic switching starts to happen. And if we further increase the current, extend to the entire whole bar device area. And if we reverse the current direction, the switching polarity also changes. So this consists with the mechanism of the spin to orbit torque based switching. And also, if we carefully compare the stray field pattern at point A and also at point age, which is after an entire hysteresis loop go back to the zero current, we can see that the straight field pattern doesn't go back to the exactly same configuration. So this suggests that the switching is not fully reversible. And other mechanisms, for instance, Joule heating, may also contribute to the electrical controllable spin dynamics of magnet switching. All right, so these are our measurements based on NV center. And I have shown you that NV sensing diamond is a two-dimensional quantum sensing platform. So in order to enable nanometer scale NV to sample distance, we have to play many tricks, for instance, making fabricated diamond nanostructure to prevent the dust between the sensor to the material. So one question is, can we actually use sensor in two-dimensional material system that's atomically flat and thin? So this can potentially enable atomic scale detection sensitivity and image resolution. So thanks for the pioneer work. The answer is yes. So people find that spin defects in hexagon boron nitride, for instance, boron-Wilson centers, shows very similar properties as NV center. So boron-Wilson center is first discovered in 2020. And people have shown that it shows very clear optical detected magnetic resonance. And we can use that to measure the electric field, use that to measure the external magnetic field, electric field, temperature, blood pressure, and also microwave field and the dynamic field environment. So next question is, can we use color centers in hexagon boron nitride as the wide field imaging platform to achieve nanoscale imaging of quantum material? So here we transfer the HBN nanoflake containing the boron-Wilson centers on top of van der Waals magnet, ferromagnet candidate, iron, germanium, tellurium. So it's a layered material system. We can exfoliate to make it very thin, and then we can transfer very thin HBN nanoflake on top of the FGT. So typically we can use HBN as a capping layer to prevent this material from oxidation. And also we can use this as a sensing layer to imaging the stray field generated from the FGT, which is shown here. And from the stray field map, we can also obtain the magnetization maps of the FGT with nanometer scale spatial resolution. So this is our static field imaging. We also find that we can use hexagon boron nitride containing color centers to imaging the spin fluctuations of these quantum material system. And we noticed that the spin fluctuation shows the maximum value around the 200 Kelvin. That's the Curie temperature of the FGT. So this suggests that we can also use HBN to imaging the quantum phase transition and to study the magnetic material system. And also we can, in the future, it will be very promising to study HBN in the ultra thin limit that can potentially enable atomic scale detection sensitivity and image resolution. All right, so finally, I would like to talk about another application of NV center, the application in the area of quantum computing. So as we discussed in the very beginning, so we show that NV center holds long coherence time and high working temperature. So this makes NV center a very promising qubit system. However, so far, the application of NV center and other color centers with accessible spins shows very limited application to quantum computing. And the limitation is the scalability of NV center. So by scalability, I mean that we want to locally control the individual NV spin qubits. However, so far, the control method of the NV center always requires microwave fields generated by oscillating current in a stripline structure. So we know that Oyster field typically decays very slow in the space. So it's not a local control method. And in addition, if we want to enable entanglement between the MV center to enable like complicated quantum operation, so this requires we put two MV center really close as 30 nanometers. So over such small MV distance, it's impossible to control the MV center individually using the conventional method. So now we need to solve the problem that we want a more scalable MV spin qubit control platform. And so far, there are many kind of material system has been studied or proposed that can serve as a quantum spin transducer to enable efficient control of the MV spin qubit or long-range qubit entanglement. For instance, using mechanical control or measurement based on MV center coupling with magnetic domain wall, as well as using magnetoelastic interaction or spin wave modes or ferromagnetic vortice systems to control the MV spin qubits. So far, the desirable scalability has not been realized. And our approach is to enable coherent, local, and voltage control of the MV spin qubits in a very similar way as we control the semiconductor qubits, where the qubit system is controlled by the electric field generated from the pattern electrode. And because the electrode can be as small as tens of nanometers, so this provides a very local and a scalable platform for us to control the qubit. And to enable the local control, we find that the key is instead of driving MV center using Earth field from the current, we can drive MV center using the oscillating stray field generated from the resonating magnetization on the ferromagnetic resonance condition. So in this case, it's drive the MV center using the stray field, which decays much faster in space than the Earth field. So this enables local control. And to enable voltage control, we can take advantage of the voltage controlled magnetic anisotropy in a magnetic pillar junction. So by applying radio frequency voltage across the junction, it can induce the variation of the anisotropy of the free layer, and this induces the resonance of the magnetization in the free layer, and this generates oscillating stray field that can be used to coherently drive the MV center. So then we study the hybrid device properties. So we can see that the ferromagnetic resonance of the magnetic pillar junction across with the MV center frequency at 400 Gauss. So this is the frequency and the field environment we can operate our quantum device. Then we will monitor the spin state of MV center by monitor the photoluminescence as a function of the radio frequency voltage, so we can study the coupling between the MV center and the spintronic devices. So we indeed observe a very clear Rabi oscillation frequency, Rabi oscillation of the MV center as a function of the duration of the radio frequency voltage applied across the junction. So this suggests that indeed the MV center coherently rotate between two quantum states induced by the electric field in the hybrid device. And also we find the Rabi oscillation can be tuned by apply a bias voltage across the junction. So this is because the bias voltage control the magnetic anisotropy. So this change the ferromagnetic resonance frequency of the device. So this controls where it crosses with the MV center. So this enables basically like electrical control of the coupling between the MV center and the spintronic devices. And also we can use our wide field imaging techniques to imaging the microwave field generated from these hybrid devices. So we can see that indeed, basically the oval shape is the boundary of the magnetic pillar junction. And we can see that the microwave field generated from the junction confined very locally, is only appear on top of the junction. And also we can turn on and off the microwave generation by using the bias voltage. And if we take a line cut along the width direction, we can see that the microwave field decays very local in the space. So it decays much faster in space than the Earth field generates from the current in a strip line structure. So this demonstrates that indeed our hybrid device can enable nanometer scale, local control, and voltage control of the MV spin qubits. And in industry, the state of art of MTJ, the size is around tens of nanometers. So if we, in the future, using smaller magnetic pillar junction, it can further improve the scalability, and it can enable a scalable quantum operational platform based on the MV spin qubits. All right, so finally, I would like to summarize my talk, and I hope I can convince you that MV Center is a very versatile quantum sensing and imaging platform to study quantum material, and also color centers in two-dimensional material can potentially enable atomic scale detection sensitivity and image resolution. And by combining MV Center with other spintronic devices, we can enable efficient and local voltage control of the MV spin qubit. So in the future, it will be promising to investigate the coupling between the MV Center and the quantum material to improve the performance of the MV spin qubits in the quantum network. So if you are interested in our research, feel free to read the published paper from our group, which is listed here. And so finally, I would like to acknowledge the funding support and also the students and the collaborators that are essential for this work. So thanks very much for your attention. Feel free to let me know if you have any questions.
Wow.
Thank you.
Amazing talk. I really enjoy your talk, and I think my group also enjoy. You receive a lot of claps over here. So
Thank you.
I open the session questions now. I have a few questions actually, but if anyone want to start, or I can start. Okay, I can start. So for the case of the antiferromagnetic imaging, so I suppose when you mentioned that in the case of a fully compensated antiferromagnet, a better option might be a ferrimagnet.
Sorry. So you're talking about the fully compensated antiferromagnet?
Yeah, in the fully compensated, you have a straight field zero, and it's going to be difficult to see or to observe the domains. So that could be, I don't know, better if you see a ferrimagnet, probably.
Yes, so you're right. So ferromagnet, you don't have this anti-parallel spin configuration over the atomic length scale, so it would be better to imaging.
In a ferrimagnet, I mean.
Oh, ferry, yes, it's the same thing. So as long as you have uncompensated moment,
okay,
it will be used to imaging the straight field.
Okay. Also, in the case of the manganese treating, in the imaging, when you send or you inject a current in the cross or in the intersection of the Hall bar, you maybe the next slide, can you switch there? In image C, you have that the first part that switches the magnetization is the central part. This might be due to the current distribution, current density distribution.
Yeah, exactly. So it's a very good point. So the current density is larger on the two ends than in the center. So that's why it starts to switching at the location where the current density is stronger, right?
Okay. And you also mentioned that you might have influence of the Joule heating. So probably you can solve this by waiting before the measurement, or it's not that simple?
So from we suspect they will be Joule heating mainly due to the fact that the switching we observe is not fully reversible. So we still see that if we go through the entire loop and go back to the same location, the stray field doesn't go back to the same location. You can see there are some small changes. So that suggests that because if it's fully spin orbit torque, we expect is just a fully deterministic. But here we notice still there are some feature that's not reversible. So this suggests maybe the heating contribute to, or other mechanism that's not reversible contributing to this switching.
Okay. Good. Thanks. And continue with the 2D materials. You mentioned that you can also create boron vacancies, right? And
yes, yes.
Is there, or what is the limitation in 2D materials to fabricate a quantum sensor? For example, is it possible to take a graphene layer and create vacancies, or antimony 2D layers to create vacancies to do some quantum sensors?
So yeah, this is a very good question. So I think there are many like single photon emitter observed in two-dimensional material, like especially like TMDs or hexagon boron nitride, and some of the single photon emitter has no basically spins. Yeah, it's just a single photon source, but we don't know because it has no spins. We cannot use that to quantitatively measure basically field or some like other property like NV center, or like use this as a spin qubit. So far basically the spin defects in two-dimensional material, I think the boron vacancy center is one of the known one. Other type of photon emitter in the two-dimensional material, so far people don't know what the spin properties and whether it has single spin or not. So I would say this is only recently discovered that some spin defects in the two-dimensional material can be used as a sensor. So I think it depends on basically like the frequency of the defects, whether it has spins, and whether the energy of the resonance is kind of detectable. Yeah, so it's a kind of find a reasonable quality one is not that easy, right? So right now we only find like boron vacancy centers as a promising system.
Okay, thanks. And I think there is one question in the seminar room.
Yeah, I wanted to know. Thank you, Chunhui. Very nice talk. I don't follow much of what you're saying, but let me ask you one thing. How's the experiment performed? Because you have to have one single nitrogen vacancy in your SPM probe. And how do you excite it and measure it? You have a sketch there that says laser microwave readout in that image.
So right. So for the setup, so first we are using ensembles of the spin defects in let's say boron vacancy centers in HBN is not a single. So far, single spin defects in HBN has not been confirmed. So in this case, we use ensembles. Basically, has the color centers everywhere in HBN nanoflake. for the wide field imaging. And basically the setup is we have a laser that we're gonna focus to the objective, so it has a wide field of view on the material system. And then we also detect the photoluminescence generated from basically the HBN using a camera. So it connects the photoluminescence or generated from these color centers at each pixel. And then we perform basically the spin resonance measurement. So we vary the microwave frequency and monitor the photoluminescence. And from that, we can get the MV, basically electron spin resonance of the color centers. And from that, from the Zeeman splitting, we can measure the stray field locally. So at each pixel, we have a spectrum, and we obtain the field.
Thank you.
Thanks.
Yeah.
Is there any other question from the participants on Zoom, maybe? If not, I have a final question. You mentioned that for the excitation of the magnetization in the MTJs, I suppose you use a similar setup to the STFMR, right?
Yes. Right. So basically we do STFMR to measure the voltage across the MTJ.
Okay. Okay. Good. Thank you very much, Chunhui, for the very nice talk.
I'm sorry, can you please, now that we're here?
Yes, please, Anna, go ahead.
Sorry,
Yes.
now that you came to this slide, I want to ask you about this graph because I didn't understand good the one in the right.
Sorry, which one? This graph, this figure?
The one in the right?
Oh, okay, okay.
Yes,
So
yes, the
so
F plus and the
basically,
F minus.
right. So basically, this is not MV measurement. This is basically we apply a radio frequency voltage to induce the precession of the free layer, and we measure basically using the basically spin torque FMR geometry that basically we send the voltage and we induce the FMR, and then this will generate mixed voltage that we can measure. So we monitor this STFMR signal as a function of magnetic fields and the frequency, so we can get the resonance condition of the free layer of this MTJ. And then because we want basically to operate the hybrid devices, it requires that the microwave field generated from the FMR precession match the MV electron spin resonance frequency, so it can drive the coherent rotation of the qubits. So in this case, we want to find kind of sweet spot that the FMR frequency match with the MV frequency. So based on the STFMR results, we find the FMR frequency across with the MV frequency at 400 Gauss. So this will be the field we can use basically the field from the hybrid device to drive the MV center.
Yes, thank you so much. Got it.
Yeah. Thank you.
Now that you give more details about this Chunhui, so when you change your magnetic field, you will lose your signal, right? So you will only have one magnetic field value to detect the
yeah. So right. So it's a very good point. So basically this is what you mentioned. So what we do is we basically vary the magnetic field. So this varies the MV frequency, the MV electron spin resonance frequency. So you can see that when the frequency match the FMR frequency, we see a peak And if it's away from it, we see the Rabi oscillation decrease. So it's not very narrow because the width of FMR, I think it's like 100, 200 megahertz. So over those, so there is kind of a magnetic field window we can operate device, and we can also control to make this operational frequency wider by adding a biased voltage, because it changed the anisotropy of the system. So it changed basically the FMR dispersion. So it's kind of changed where the FMR cross with the NV-ESR. So basically we can further basically control basically the Rabi oscillation electrically.
I see. Okay. Good. Thank you. I think Pablo has a question. Please go ahead.
Okay, thank you. Thanks for the talk. I arrived a little bit late to your talk, so I wonder if you did some comparison between whole squid magnetometry, scanning squid magnetometry with your scanning technique in terms of resolution, spatial resolution, and magnetic resolution.
Yeah, so scanning squid, there's several types of scanning squid. So one is like a micron-sized scanning squid, and the resolution is on the range of 1 micron. And also there's another type of scanning squid that's developed by like Wiseman in Israel group. So nanosquid, the resolution is better on the range of sub 100 nanometer. So I would say the field sensitivity of both squids, like nanosquid and the scanning squid, is able to imaging, like for instance, single electron spins, and both the limit of the field is around like nanotesla range. So in this case, the field sensitivity of MV center and the squid is probably comparable. One of the advantage of MV center is it allows to measure the high frequency field, where the squid is probably limited to like very low frequency like kilohertz or megahertz. However, MV center is able to measure microwave field or magnetic field fluctuation like noise up to like a gigahertz range. So that's maybe the one of the advantage of MV center. And also there are some other model for quantum sensing based on MV center. For instance, it can also measure temperature, pressure, and electric field. So for the squid, I think it can measure the temperature pretty well. MV center can measure basically various different physical properties of quantum material.
Okay, thank you.
Yeah.
Thank you, Pablo, for your question. I think there is no more questions. And okay, so with that, thank you again, Chunhui, for sharing your work with the group. You are welcome to share whenever you want.
Okay, thanks.
I will stop recording now, and thank you. See you next time.
All right. Yeah. Thanks. Thanks, Luis. Have a nice day.
Yeah, you too.